Hello again, and welcome to our lecture on complex numbers. I think you'll find this lecture fascinating, perhaps even strange. Complex numbers are a lot different than what we've been talking about so far with the real numbers. But they will permit us to factor polynomials. And also near the end of the lecture, I'll show you some really beautiful pictures of things called fractals. So that will be near the end of the lecture. So let's get started with the motivation for complex numbers. Recall when we studied polynomials that some polynomials don't have real roots. They can't be factored over the real numbers. A very simple example is x squared plus 4. You just can't factor that polynomial over the real numbers. It doesn't have real roots. The graph of x squared plus 4 does not touch the x-axis, does it? Well, to get an idea of how complex numbers work, let's go back actually to another of the examples I did earlier. Was a little more complicated, but we looked at this example in great detail. And now with aid of the new complex numbers, we'll get a better feel for this example. It was the polynomial x squared minus 2x plus 13 over 4. And if you remember, we used the quadratic formula to write the roots as 2 plus or minus the square root of minus 9, all divided by 2. And then we factored out a 3 from the radical. 9 is 3 squared. And so we now can write it as 2 plus or minus 3 times the square root of minus 1 over 2. And if you want, you then can split it into two pieces. 2 over 2 is 1, and 3 over 2 is 3 halves, square roots of minus 1. And again, there's that plus minus sign. Well, this was an unfortunate occurrence because square root of minus 1 doesn't exist in the real numbers. So what did mathematicians do? They invented a new system of numbers. They called the square root of minus 1 I. And this is the definition of the imaginary unit I. It's defined to be the square root of minus 1, or it's a number such that I squared is minus 1. I is not a real number. We're extending the real numbers to a bigger set of numbers. In fact, if you add the real numbers together with real multiples of this imaginary unit I, you obtain what we call the complex numbers, or the imaginary numbers. Each complex number can be written in standard form a plus bi, where a and b are both real numbers. Okay, a little complicated. Let me talk a little more about some of the terminology, and then we'll do some examples. In particular, given a plus bi, if b is 0, then the number is real. A plus bi would just be a, and then the number is real. And if b is not 0, then the number is an imaginary number or a complex number. So you see that the set of real numbers is contained inside. It's a subset of this larger set of complex numbers. Now, complex numbers, amazingly enough, don't play a major role in pre-calculus or calculus. We'll use them today, and we'll use them a couple of more times later on. But if you go on and take a calculus class, you probably won't see much about complex numbers until after calculus. And then they come in to play a major role in engineering, physics, and higher mathematics. Okay, that said, I think it's important for us to get a feel for these complex numbers and to practice with them. So let's do some computations. Square root of minus 9, we saw that in the previous example we were talking about. Let's simplify that and write it in standard form. Well, 9 is 3 squared, so it can be written as square root of 3 squared times minus 1. Bring the 3 outside the radical, and you get 3 times the square root of minus 1. And remember, square root of minus 1 is I, so it's 3i. How about square root of minus 16 plus 5? Let's write that in standard form. Well, first of all, flip-flop and write it as 5 plus, well, 16 is 4 squared, so it's 4 squared times minus 1. So it's 5 plus, and now I can bring the 4 outside the radical, because 4 squared is 16. And I have 5 plus 4 square roots of minus 1, and of course that's 5 plus 4i, now written in standard form. Let's do some operations with complex numbers. You can add them. For instance, let's add 2 plus 3i together with minus 3 plus 2i. The good news is you just add them as you would normally. You add the real parts, 2 plus minus 3 gives minus 1, and then you add those imaginary parts, 3i plus 2i is 5i. So adding complex numbers is pretty simple. But let me show you another kind of curious example. Let's add 7 plus 3i together with 7 minus 3i. And look what happens. The 7 plus 7 is 14, but the 3i cancels with the minus 3i. Well, what's happened here? You see the relationship between these two complex numbers? Those are called conjugates of each other. The definition of a conjugate is if you have the complex number a plus bi, its conjugate is a minus bi. And the sum of a complex number and its conjugate turns out to be real. Let me do another example for you. 3 minus 4i plus 3 plus 4i. Well, the 4i's cancel and we're left with just 6. Okay, let's go back to that old example again and now write the answer using complex numbers. Remember, our polynomial was x squared minus 2x plus 13 over 4, and we wanted to find the zeros. And we used the quadratic formula, and we obtained that x was 2 plus or minus 3 square roots of minus 1, all divided by 2, and that's 2 plus or minus 3i divided by 2. And now, using that plus minus, you get two answers. You get two zeros. The first one is 2 over 2 plus 3 halves I, and the second one is 2 over 2 minus 3 halves I. Those are the two zeros of that quadratic polynomial, and notice they are complex conjugates of each other. That's always true if the polynomial has real coefficients. So what's the history behind these weird complex numbers? Well, it turns out that Cardano, when he was studying how to solve cubic and fourth-degree polynomial equations, introduced complex numbers as a tool for solving these equations. Later on, the symbol I for the square root of minus 1 was introduced by the famous mathematician, very prolific mathematician, Euler. Okay, we know how to add complex numbers. What about multiplying them? So let's do an example. How about 2 minus I times 4 plus 3i? How do you multiply two complex numbers together? Here's the good news. You do it as normal. In other words, you just multiply out the four terms. So let's do it. 2 times 4 is 8. 2 times 3i would be 6i. Minus I times 4 is minus 4i. And now comes the only tricky part. Minus I times 3i is minus 3i squared. But wait. I squared is minus 1, isn't it? So that's actually going to be a real number in a moment. So let's go to the next line. It's 8. 6i minus 4i is 2i. And then minus 3i squared is minus 3 times minus 1, which means plus 3. And so your final answer is 11 plus 2i. So the only thing to keep in mind here is when you multiply complex numbers, whenever you see I squared, replace it with minus 1. Now, we've talked about complex conjugates. What if you multiply a complex number by its conjugate? Well, let's see what happens. How about 3 minus 5i times 3 plus 5i? Those are conjugates of each other. Well, you notice that the middle terms, 3 times 5i, cancels with the other middle term, minus 5i times 3. And so you're left with just 3 times 3, or 9, and then minus 5i times plus 5i, or minus 5i squared. So it's 9 minus 5 squared is 25, I squared, and then you get 9 minus 25 times the square root of times minus 1, because I squared equals minus 1. And so the final answer is 34. Something interesting here has happened. A complex number times its conjugate is always a real number. That will come into play later on in this lecture. Complex number times its conjugate, the complex parts disappear, and the final answer is a real number. Now, complex numbers permit us to find the roots of quadratic polynomials. In fact, now the quadratic formula is, we can use it even though we're taking square roots of negative numbers. We just convert those to complex numbers. But we can go a lot further. We now can take any polynomial of any degree and factor it into linear factors. This is called the fundamental theorem of algebra. Let me state it for you. If f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors. In other words, the polynomial can be factored. And it can look like this. F of x will be some coefficient in front, let's call it a sub n, and then it has n linear factors, x minus c1, x minus c2, x minus c3, all the way down to x minus c sub n. Those c's are complex numbers, and those are the zeros, the roots of that polynomial equation. Now, those c's could also, in some cases, of course, just be real numbers, or they could even be repeated. But the bottom line is, given a polynomial of degree n, theoretically, you can factor it into n linear pieces. This theorem was first proven by Gauss. Gauss lived from 1777 to 1855, and it's kind of amazing. He proved this theorem in his PhD dissertation at age 22. Gauss is often thought of as being the greatest mathematician of all time. He did important research in all areas of mathematics, including one of my favorite areas, non-Euclidean geometry. Okay, so given the fundamental theorem of algebra, in theory, we should be able to factor any polynomial into linear factors. Now, I've said earlier, and it's still true, it's difficult to do that. But let me show you an example that will illustrate the theorem. You'll see how it works, even though this example is fairly straightforward. In general, given a giant polynomial, it's extremely difficult to factor it. But here's a simple example. Let's look at the polynomial x to the fourth minus x squared minus 20. According to Gauss's theorem, this should be able to be factored into 4 linear factors because it's a fourth degree polynomial. Well, I can do a pretty simple factorization as x squared minus 5 times x squared plus 4. You can check that I factored that correctly by multiplying it, and you'll see that you get the original polynomial. Okay, so I'm down to quadratics. Well, what about x squared minus 5? Does it factor? Yeah, if you're allowed to use radicals, it factors into x plus square root of 5 times x minus square root of 5. So I've taken care of that first quadratic term. What about x squared plus 4? Now I need complex numbers, don't I? The roots to that are 2i and minus 2i. And so now it's fully factored as x plus root 5, x minus root 5, x plus 2i, and x minus 2i. If you have the stamina, multiply that out, those 4 terms, and you'll get the original polynomial. And notice there are 4 linear factors here. The zeros are plus or minus square root of 5 and plus or minus 2i. One thing we've noticed here, and in that last example we noticed it, that the zeros of polynomials, polynomials with real coefficients, occur in conjugate pairs. In that previous example, 2i and minus 2i are complex conjugates of each other. And it goes without saying, or it's worth saying again and again, factoring can be very difficult. Graphing a function might help in getting an idea of how to factor it, but in general, factoring polynomials is not an easy skill. Now, we've talked about complex numbers and how to multiply them and add them and things. Here's some sad news. Not all the properties that we've learned to love in algebra hold for complex numbers. Let me give you an example of that where you have to be a little careful, a little pitfall with complex numbers. Remember, with real numbers, the square root of a product is the product of the square roots. Well, that's not true anymore with complex numbers. Let me show you an example. Let's look at the square root of -4 times the square root of -9, and I'll show that's not equal to the square root of the product -4 times -9. So the left-hand side, the square root of -4 is 2i, and the square root of -9 is 3i. But what about the other side? Well, -4 times -9 is 36. So the right-hand side is square root of 36. Okay, what's the left-hand side? 2 times 3 is 6. I times I is -1. The left-hand side is -6, but the square root of 36 is 6, so they aren't equal to each other. Okay, we've done this before. Let's do it again. You be the teacher. Here's what your task is today. You're making up another test. And now you want to find a polynomial, say of degree 4, with certain a polynomial with real coefficients, and it has certain zeros. You'd like to construct a polynomial, say, with zeros -1, -1, and 3i. What should that polynomial look like? Well, if -1 is a 0 and it's repeated twice, then you'll have two terms, x plus 1, x plus 1. Now, what about 3i? 3i, if that's a 0, then -3i, its conjugate also has to be a 0 because we want our polynomial to have real coefficients. So we get x plus 1, x plus 1, x minus 3i, x plus 3i. 4 terms. And then you multiply this out. I won't bore you with the details of multiplying it out. It's a non-trivial task. But when you do that, here's the final polynomial you get. X to the 4th plus 2x cubed plus 10x squared plus 18x plus 9. So you're the teacher. And on the test, you plop down that polynomial of degree 4, all multiplied out. And you ask your students to find the zeros. Ouch. Tough question, isn't it? It's pretty easy to construct the polynomial, but now to factor that without knowing the zeros ahead of time, pretty tough going. Okay, let's do another operation with complex numbers. We know how to add and multiply. How about dividing? This is pretty simple, actually, but it can be a little bit messy. Let me show you how it works with an example. Let's take a quotient of two complex numbers. How about 2 plus 3i divided by 4 minus 2i? Well, the secret here is to multiply numerator and denominator by the conjugate of the denominator. Because remember, a complex number times its conjugate is real, and that will get rid of the complex number in the denominator. So when I do that, I multiply 4 plus 2i divided by 4 plus 2i. The numerator becomes 8 plus 4i plus 12i minus 6, and the denominator becomes 16 plus 4 when you multiply that out. And then simplifying the numerator, you get 2 plus 16i divided by 20, and then we can split it apart and write it in standard form, 1/10 plus 4/5 I. That's the quotient of those two complex numbers. Kind of difficult going because it required some multiplication by conjugates and then some simplifications. Okay, great. I'm comfortable now with our ability to manipulate complex numbers. Let's turn now to a beautiful application of mathematics and of complex numbers. This is great stuff. You'll like this. We're going to talk about fractals and the famous Mandelbrot set. And in order to do that, we first have to know how to graph complex numbers in the plane. And here's how it works. Imagine the x-axis, the old x-axis. That'll now be what's called the real axis. And then the vertical axis will be the imaginary axis. And a complex number a plus bi is plotted in this plane as the ordered pair AB. Let me show you some examples. We're going to plot on the complex plane the numbers 2 plus 3i, minus 1 plus 2i, 4, and minus 3i. Here they are. Here's the complex plane. Let's look at, say, 2 plus 3i. Notice that the real coordinate is 2, so I move 2 units to the right, and then I go up to 3i. So that's the ordered pair 2, 3, which corresponds to the complex number 2 plus 3i. Over there on the other side, you get minus 1 plus 2i. That's minus 1 and then go up to 2i. The complex number minus 3i is actually on the imaginary axis at minus 3. And then over to the right, you see the point 4. It's the real number 4. So we know how to plot complex numbers, don't we? If I give you a complex number, you know how to plot it now. Okay. Now, this complex plane can become sort of an easel in which you can draw stunning pictures called fractals. One of the most famous of these fractals is called the Mandelbrot set, and it's named after the Polish-born mathematician Benoit Mandelbrot, who was born in 1924. Let me show you how the Mandelbrot set works. It's amazing. I think you'll really like it. What we're going to do is look at each complex number in the complex plane and ask the following question. Is it in the Mandelbrot set or is it not? And here's the rule for being in the Mandelbrot set. Slightly complicated here, so bear with me. Pick a complex number, C. We'll call it C. So it's some point in the complex plane. And you form a sequence of numbers. A sequence of complex numbers. The first number is C. The next number is square it and add C. So it starts at C, you square it and add C. That's the second number. The third number is square that guy and add C. So I square it and add C, and I have this new number. I square it and add C. It can be kind of complicated to do this, but I think you see the pattern. You start with C, square it, add C. Square that and add C. Square that and add C. Now, for some values of the complex number C, for some complex numbers, this sequence, boom, 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 is bounded. And by bounded, we mean the following. It never gets too big. It never goes too far away from the origin. It stays sort of in a region near the origin. But for other complex numbers, when you form this sequence, the number heads off very large. It goes far away from the origin. We call that unbounded. And if you're bounded, you'll be in the Mandelbrot set. And if you're unbounded, you aren't. All right, let's get our hands dirty. Let's actually analyze some complex numbers and see if they're in the Mandelbrot set or not. All right, how about minus 2? That's a complex number. It's actually real. Is minus 2 in the Mandelbrot set? Well, you form this sequence. Remember how it works. Minus 2 is the first number. You square it and add minus 2, the original number. So I get minus 2 squared plus minus 2. That's 4 minus 2, or 2. I then square that number and add to it minus 2. So I get 2 squared minus 2, or 2. Whoa, that's the same number as before. I do it again and I get 2. I do it again and I get 2. This sequence is kind of dull. It goes minus 2, 2, 2, 2, 2, 2 forever. It's bounded. It's not going off really big or anything. It's staying very close to the origin. So minus 2 is in the Mandelbrot set. Okay, good going. Let's see if we can do another one. 1 plus I. We know where that is in the complex plane. Is it in the Mandelbrot set or not? Let's find out. What do? You start with 1 plus I, you square it, and add to it 1 plus I, the original number. Then you take that, square it, and add 1 plus I. So let me do a few of the steps. The first one is 1 plus I. The second one is 1 plus I squared plus 1 plus I. And if you work that out, you get 1 plus 3I. You take that number, 1 plus 3I, you square it, and add 1 plus I. Trust me, when you do that, you get minus 7 plus 7I. Got a little bit bigger, didn't it? The next term turns out to be 1 minus 97I. I don't recommend that you actually do that computation. Trust me, that's what it is. And it gets worse and worse. The numbers get bigger and bigger. The coefficients start getting enormous. This is unbounded. This is not in the Mandelbrot set. 1 plus I is not in the Mandelbrot set. How about another one, just to see how good we are at this? How about the number I, the complex number I? Is it in the Mandelbrot set? Let's find out. Let's do the computation again. I, and then you square I and add I to it. Well, I squared is minus 1, so the next term is minus 1 plus I. You then square minus 1 plus I and add to it I. And you get, when you do that computation, minus I is your final answer there. Then you square that and add I to it, and you get minus 1 plus I. How interesting. We've come back to where we started from. We're back to the second term, haven't we? We're starting to repeat ourselves. This sequence is a little more interesting than that first sequence. It goes I, minus 1 plus I, minus I, minus 1 plus I, minus I, minus 1 plus I, minus I. It goes back and forth. That's in the Mandelbrot set because it's bounded. It's not going off really far away from the origin. It's just going back and forth. So it's in the Mandelbrot set. Okay. So with this definition, you can imagine a computer doing this for thousands, millions of complex numbers. And each time computing that sequence out to 1,000 terms and seeing whether or not it's bounded. And if it is bounded, it's in the Mandelbrot set, and we could then paint that complex number with, say, a black dot. So we'll call a complex number a black dot. We'll paint it black if it's in the Mandelbrot set. And if it's not in the Mandelbrot set, why don't we say paint it blue? And so we have a picture now of the numbers in the Mandelbrot set. That'll be the black part of the picture, and then the blue part of the picture will be the numbers that aren't in the Mandelbrot set. And here's the picture of the Mandelbrot set. Isn't that impressive? Wow. To me, that's one of the most beautiful pictures in mathematics. This picture has amazing properties. If you zoom in close to some of those little things sticking off, you see that the picture starts repeating itself. It's self-similar. The Mandelbrot set has many, many very interesting properties. And then mathematicians have developed other fractals. Beautiful pictures. And if you go to the internet, I'm sure you can find many of them. Let me show you a few pictures of fractals. These are all similar to the Mandelbrot set, but with slightly different rules. And you can see that you get some amazing graphics with these pictures. Okay, good. I hope you enjoyed that piece about fractals in the Mandelbrot set. It's a fascinating area of mathematics, a fairly new area of mathematics. It's only a few 10, 20, 30 years old, and yet it's now an area of much research. And in my department, for example, we teach courses on fractals at the graduate level. But we were able, just with our study of complex numbers, to get a feel, I think, for how fractals work. So what are we going to do next time? Our next lecture, we'll turn to a new class of functions. We'll look at a class of functions called rational functions. Rational functions are nothing more than quotients of two polynomials, polynomial divided by polynomial. And we'll talk about the usual properties of these functions. What are their domains? What do their graphs look like? And of course, we'll have some interesting applications of these rational functions. So I'll see you next time when we talk about rational functions. Thank you.